Okay, I'll try to not be too loud. Does this work for everyone? Can you hear me? Not yelling too much? Awesome. Good morning. Thanks a lot for coming out to my talk. I'm really happy to be back at 360 Startup. I gave my first talk here last year. And the direct outcome of that was that I spoke to attendees afterwards and actually built an open source library that became pretty successful. So far this conference has a pretty big impact on me, and I'm really happy to be back. My name is Encz, and I'm a software engineer at Polymorphism in San Francisco. That's the blue logo. And since the beginning of the year, I've been working a little bit more open source. And one of the more popular frameworks that I've worked on was Swift. And that is the orange logo you can see. And that is the library that basically was born out of the last 360 Startup talk that I gave last year. Today I want to talk about something different, and the title of the talk is Leveraging Swift's Type System. The goal of this talk is kind of to condense the experience that I gathered over the last 2 years working with Swift and Swift's type system, and hopefully convey it in a way that is useful to you. If you're not bought into Swift and you still prefer working on Objective-C, maybe because of the type system, then I hope that one of the outcomes is that I convince you a little bit more that there actually are a lot of useful features in there. If you're already very familiar and comfortable with Swift, then I hope there's maybe some concepts you haven't heard about before, or there's something else inspiring this talk. I kind of broke it down into 3 main sections that I want to talk about. The first one is a really fundamental one. I'll be talking about types throughout the rest of the 45 minutes. I think it's important to have a little bit of a brief history, where types come from, why they're useful, and how we use them today. The other 2 sections are going to be much more practical. There I want to focus on specific techniques in Swift and Swift's type system that can help us to write at least what I consider better software than we did in Objective-C. And then I want to break down into two categories. The first one is correctness and documentation. There I want to focus on tools that can help us at compile time to prove at least certain aspects of the program and make sure that we can avoid the most obvious mistakes. And that also goes hand in hand with documenting our code better. We'll see why. And then the last section I want to talk about is how the type system in Swift has kind of changed how design code at a higher level, to how to decide which types get which responsibility, and so on and so on. So we'll go a little bit of a higher level of abstraction. Let's start off with why we have types in the first place. And for that, I think it makes sense to go back in history a little bit. And we go back to a time before we had compilers, and before we had types, and where we had to write code in assembly. What you can see here is Margaret Hamilton. She was the lead software engineer on the Apollo 11 mission, the first mission that sent people to the moon. And frighteningly, a really important part of that was a huge pile of assembly code that actually sent that space shuttle up there. I had assembly in school a little bit, but I didn't really write a lot of assembly code since. But to me, it's always really scary to read assembly source code. One of the problems of assembly source code is that it's really unexpressive. And you can see it here on the right-hand side, it's really small. But even if you don't read assembly code, the rightmost column is the comment column. And what you'll notice when you look at this code is there are more comments than there's actual source code. The language itself is so inexpressive that not even the best assembly developer will understand what is going on just by looking at the instructions. And furthermore, a really big problem with assembly is that it's really tedious to write. From people that I talk to that write a lot of assembly, apparently it's not that hard, but you have to write a lot of code because you operate on such a low level of abstraction. Since that time, almost 56 years ago, we luckily moved on to higher level languages that we can use that make us much more efficient, that are more expressive, and basically write a lot of this code automatically for us. Now you might wonder how that ties into types. Types are essentially a really essential part of enabling higher level languages because the compiler needs a way to understand our intent and to generate the right machine instructions from that. One part of understanding our intent is a really important part of encoding types inside of memory. So you look at memory, what we have is just 1s and 0s and bits. When you worked in assembly, you would manually move these bits around, and you would remember which bit has which meaning. So it was basically the responsibility of the developer to understand then if something was a bool, or maybe it was intended to be a string or a number. In higher level languages, we have this understanding as part of the programming language and the compiler. We define data types, and these data types have a certain encoding. And when we write in higher level language, then the compiler generates instructions that generates code that will store these types in memory according to that encoding that has been defined. So types are really essential for compilers and for higher level languages. Without types, we wouldn't have them today. Here's an extremely simple example from Objective-C code that uses types. And what we're doing here is really just using two local variables. We're creating one with an integer, we're creating a second one, and then assigning the value from the first to the second. In assembly, this would be a lot more code, but in higher level language, as I said, the compiler can generate that code for us. And as part of that, it has to understand the types, so that it knows, for example, in this case, how much space it has to allocate on the stack. It has to know that int has a certain size, it might be 4 bytes, 8 bytes, depending on a lot of factors, but it needs that information. And as part of what a compiler does, as side effect is that it also validates certain aspects of our program. So it is trying to generate machine code from a higher level language, and as part of that, it also checks in some cases if it can actually generate a valid program or not. And depending on how powerful your type system is, the compiler will do more or less correctness checks. The Objective-C compiler does fairly little correctness checks, especially compared to Swift, because it's really just a pretty thin wrapper around C. But on this slide, I have a couple of examples of things that actually get verified at compile time. The first example is we have two object pointers. The first object pointer points to a number, and subsequently we try to assign that object pointer of a number to an object pointer of type string. And here we actually get a compiler warning. The compiler will tell us that these two pointer types are incompatible. And that is really useful because assuming you're working with an NS number, but you're actually working with an NS string, then bad things happen at runtime. Ideally, we want to know that up front so that we can catch this mistake before we should. The second thing that the Objective-C compiler does for us is verify messages that we try to send to objects. If you've written Objective-C, you've probably seen this before. You try to call a method that is not declared in an interface, and that will result in a compile error. And that is really a good thing, because if this compile error wouldn't happen, if this method is actually not defined, we again would crash. So a big part of what a compiler does is avoiding crashes. But it can do it really well in Objective-C, especially when compared to Swift. A classic example that you might have experienced when you write Objective-C code is that you cannot insert nil values into collections. So if you have a dictionary, for example, you try to put a nil value in there, this will crash at runtime. We cannot express this in the type system, and that's why the compiler cannot catch this for us. So we'll write this code, and it will generate valid machine code, but that machine code will lead to a crash. Crosstalk, I'll use this angry face in places where I think now that I use Swift, that is really annoying that Objective-C doesn't have these features. So to summarize the fundamental of types, the type system really does these three main tasks. I think it defines for each type a valid set of values. So for an integer, that's just the number of integers that fit into 4 bytes, 8 bytes, etc. It also defines a valid set of operations. That, for example, can be the methods that you can call on an object. And lastly, it defines the representation, and that is typically how it maps to memory and how it's encoded. So now that we understand the fundamental of types, I'd like to go on to see how Swift can help us write better code in these two categories that I talked about. And the first one is correctness and documentation. And as an example, I want to use asynchronous error handling. It's a typical task you have to do when you write any kind of iOS or macOS app that goes to the network, fetches some kind of data. And to explain the concept here and the improvement I've seen in Swift, I'm going to start off with what they used to look like in Objective-C. So what you see here is the type signature of the callback block converted to Swift from Objective-C that you would hand into any task that has some kind of asynchronous operation that calls this block upon completion. So the first thing you'll notice is we have two arguments. One is the result, one is the error. And both of them are optional, because implicitly in Objective-C, everything is optional. The language cannot express the fact that it can be null, or they cannot be null. Therefore, we have to import them as options. We'll talk about optionals more later on. So we have this result type and error type. And one of the things you'll realize is that there's kind of weird combinations that are possible here. You could have a result and an error at the same time. The type signature allows for that. But what does it actually mean? Or you can have a result and no error. So really there are 4 possible combinations in a place where we would only expect 2. We would either expect to get a result back or an error. And to handle this correctly, you have to go back and read the documentation. And documentation actually says that you should always take a look at the result type and not at the error. So if there's a value, the operation was successful, and if there's none, it failed. If your code is implemented in a way that first checks for the error value, then you did it wrong, and there might be cases where you just discard a successful result. I learned this actually only after working on Objective-C for 2 years. So that's a great example where Objective-C really relies on this tribal knowledge, convention, and reading documentation to express something because you cannot express it in the type system. So if you worked with Swift before, you might have seen the result type. And result type was very early brought in by Swift developers that worked with other languages that had this type. The idea of the result type is to express precisely what we actually want to express in the first example. And that is the mutually exclusive case of either a success or a failure, but never both of them and never neither of the two. We do that with this generic type. It has two generic type arguments. The first one is the data that we get back in the case of success, and the second one is the error that gets thrown in case of an error. And RETWEETS is actually implemented as an enum. We're going to see that in a second. And when you try to use this enum, the typical way how you try to get the values out of that is using a switch statement. And that switch statement will force you to handle both cases. There are ways you can use syntax to actually just check for one of the two values, but the default is really to use a switch and to check for success and for failure. And I think that's a great example when you compare this to Objective-C. Swift, the compiler is basically pushing you into a direction where you can clearly handle two cases, and you'll write code that actually handles errors and success cases directly without that you have to read any additional documentation. As I mentioned, the result type is just an enum under the covers, and depending how familiar you are with Swift, you might know that is true for optional types as well. So optional type is also just implemented as an enum, and it's a special kind of enum that is called enum with associated values. And what you can do with enums with associated values is express precisely what you're trying to do. It's being mutually exclusive. Either of the two values is possible, but not both of them. And you could extend this for more examples. And the only difference between optional and result type really is that the result type has two generic type arguments, where optional only has one. So that concept is called enums with associated values, and in other languages, it's more formally known as tagged unions. So if you want to look up tagged unions, you'll find a lot of other use cases beyond optionals and result types where you can use this approach. Another tool that is pretty popular in Swift is type aliasing. Who has heard of type aliasing before? Yeah, some people. It's similar to type def in C, and it basically just allows you to rename a type for a certain context. Why would you want to do that? Well, the suite summarizes it pretty well. It's 0, 20, 24, and only one type remains, and that is string. So string is one of these ubiquitous data types that you can use in so many different contexts. You can use a string, and you should use a string to resemble a phone number, a postal code, a physical address, an email address. But all of these types actually have different semantics. They are a sequence of characters, but there are different things that are true about them, different formats, different operations you can perform on them. And we use strings usually to resemble that. So once you start working in Swift, you use the type system a lot for documentation of your code. But if you use strings in all the different places that I just mentioned, then you use a lot of that value. So what people try to do is use type aliases to rename these basic types that are used redundantly for their specific context. So a really simple example might be a first struct of two fields. One is an email address, one is a physical address. And to just clarify the context, what this type means in this context, you can use a type alias that renames a string to be called address or email. And this is really valuable, especially if you think about cases where you have a return type, and that return type doesn't have an argument label, and you see a string return type instead of email, then that is much less expressive. So if you have a function that returns email or address, you know what its type is, but you also understand the semantics. But this only goes so far, because it really is just a rename. It's still a regular string, and you still have some issues. For example, if somebody expects an email address, you could still pass in a social security number that is formatted as a string, or a physical address, and the compiler will not stop you. So you can take this a step further, and you can use something called, or what I call a wrapper type. And here in this example, you can see a very simple wrapper type, and essentially all it does is it wraps the space value and creates a construct around it with an initializer and a property that stores the space value. So this here still uses a string as a storage, but it actually has an initializer that takes in the space type, and the interesting part about this initializer is that it throws. So what we can do as part of this type is we can take in any arbitrary string, and then we can perform a validation. We can say, is this actually a valid physical address? Or is this a valid email address? And if that validation fails, we can throw an error, and we can not create a value. And we can basically encode this meaning that we have about this type, the special formatting that we require inside of the type system to some degree, by saying if someone created a value of this type, they have passed our sanity checks. So that's really a great advantage of this wrapper type. And secondly, we are now at this point to have a distinct type, and the compiler will actually warn us if we try to use it in a place where someone would expect, for example, an email address. So you don't have this ambiguity that you have in the type alias. Once I discovered this approach, I started using it so frequently that I decided to wrap it into a small library called Validated. And this library just has, it's 100 lines of code. It doesn't do a lot, but it makes it a little bit more streamlined to create these wrapper types and pack them together with a certain validation. The core of the library is a validated type that has two generic type arguments. The first one is the base type. In this case, it would be a string. And that is the type that actually acts as underlying storage. And the second generic type is a validator. And that validator takes in the base type and returns a bool, depending on whether or not the base type meets the criteria of this wrapper type. And then you get free available and throwing initializers on this type. And you can write code like this, where you use the type alias for email. Then you try to initialize the email with a string. And if it's successful, you'll get an email value. And if it's not successful, depending on which initializer you use, you get a null value or you get an error that gets thrown. And I think this is really useful. I started using it throughout my code base in a fair amount of places, because now I know when I'm dealing with email value, that it's a validated email address, and I don't have to subsequently write tests to cover that. I have it covered in one place, and I can kind of treat it as proof that I can use throughout my program. So type aliases are great. They're really helpful for moving out of this first step where we have these base types that are used in very ambiguous ways, and it helps in improving documentation. But in some cases, I think it's worth considering if a wrapper type is not even better, because you can validate semantics and you can avoid using the wrong types in the wrong places. Another cool tool in this category is called phantom types. And before I dive into what phantom types are, I want to dive into a use case. In the Planner app, that's the app that I work on most of my day, we have object UIDs for every object that we store in the client and that we sync to the server. So any piece of data that comes down that we persist locally has some kind of identifier. And that identifier is essentially just a string. And a string can point to a lot of different things. The string can identify a user, the string can identify an object like an attachment or a document. It's just a plain string. So for out of our code base, we have a lot of functions that say, give me a document with this identifier, and what it takes as an argument is a string. What I would like to see is, what does the string actually point to? And we can accomplish that with phantom types by, again, building a very simple wrapper type. And a wrapper type might look like this. It is an object UID, and the only field it has is the underlying storage, which again is a string. And it has a generic type argument that I have, for which I use the funny ghost or phantom here. And it's called a phantom type because we have this generic type argument, but you can see it's not used in any other part of the type definition. It's just up there in the angle brackets, but we don't use it to actually change anything about this type. It's just really there to disambiguate what this object is pointing to without that we actually rely on the type itself. And what this enables is to move away from a string and instead uses generic object number that actually is a string under recovers, but now has much more information than it had before. So now asking, for example, what is the current user ID? Instead of getting a string back, I now get back an object UID pointing to a user. If I want to ask, give me the annotation for a certain ID, I no longer request a string, but I'm now asking for an object UID that is actually pointing to an annotation. So if I now have a UID that is pointing to a user, I cannot by mistake pass it into the wrong function. The compiler will generate an error. So I hope these examples made sense. They're pretty small and in isolation, and I want to kind of tie them together in a bigger example that shows how we can model something with this type system in a much more expressive way than we could in Objective-C. The goal for this, what I call a case study, is to model a type that is JSON encodable. That means I want to take something that is memory, a dictionary, or an array, and I want to return it into its JSON string representation. So when a function takes a dictionary or an array and returns a string, and then I could go off and send it to a server. So what would the type signature look like in Objective-C? You would expect something like this. It would return a string, and the input type is ID. ID in Objective-C means it's an object pointer to any arbitrary type. The reason I accept ID here is that I want to use NSJSON serialization under the covers. And NSJSON serialization has the method that takes the object and turns it into a data representation. Then I can take the data representation and turn it into a string. But the argument it accepts is of ID type. And you'll see in a second why that's the case. There are actually a lot of requirements for something that can be encoded in JSON, but we cannot encode it in the type system. The main reason for that is that on the top level, we can have either an NS array or an NS dictionary. In Objective-C, there's really no good way to express that. If we can have two possible or multiple possible types as arguments, then we usually resort to the ID type, because that is the parent type of all of these. But if we read through the full list of requirements, then you'll see that we actually can't pass in any object. If I pass in an state, this will crash. If I pass in anything that doesn't fulfill these four criteria, it will result in a runtime error. And that is, the top level has to be array or dictionary. All objects have to be string, number, array, dictionary, or null. Dictionary keys have to be string. And numbers are not allowed being odd number or infinity. So if you want to deal with this API, you actually have to read this documentation because the type system gives you absolutely no information. It just says, give me any object and I'm going to turn it into JSON. And if you violate these rules, it's going to crash. So what I want to do, and what I want to do in the next steps, I actually skipped ahead a little bit too fast, is try to resemble this in Swift and move as much as possible from this documentation that lives somewhere outside of our source code into the type system. And we can actually do a surprisingly good job at that, as I found out. So let's do it criteria by criteria. And the first one is that the top-level object is either a dictionary or an array. And we've seen this pattern before, where we have values that can be mutually exclusive. And for that we can use an enum with associated values. So we can say, we have an enum that's called JSON root. There's two cases. It's either a dictionary or an array. And for now, we're using type aliases called JSON dictionary and JSON array, for which we'll fill in the definition on the next slides. But for this, we have expressed this requirement. Second requirement is all object instances are NS string, NS number, NS array, NS dictionary, or NS null. So what we need to do here is we need to annotate types that are actually JSON compatible. And to annotate types in Swift, we can use protocols. What I'm going to use here is just an empty protocol because we don't really have any requirements. There's no behavior. There's nothing that this type should be able to do. But we want to ignore these types in order to be able to validate them in the type system. So we use this empty JSON value protocol, and we annotate any type that is actually JSON compatible with it. The first JSON compatible type is JSON root, the type that we just defined ourselves. And the other two ones are NS string and NS number. We can use an extension, and we can extend these base types to let them conform to this problem. Now, the only type that is missing is NS null. I'm not going to use that one because I'm going to instead accept optional values inside of the dictionary. And before I pass them on to NSJSON serialization, I'm going to replace these optional values with NS nulls. So I can use an optional in the type system to express this requirement instead of using NS null. Let's move on to the next requirement. That is, all dictionary keys have to be instances of NS string. And here we can fill in these type aliases that are defined earlier. We can say type alias for dictionary is a mapping from string to an optional JSON value. And the type alias for JSON array is an array of JSON values. And I can use string instead of NS string because these are bridged fairly nicely. Now we have one last requirement that I will have to fulfill, and that is that numbers are not allowed to be odd number or infinity. This here is a little bit harder to prove because we can't really easily encode the type system, but it would be a great use case for a wrapper type. So what I showed you earlier, you could create a wrapper type that takes an NS number and then checks if it's not a number or infinity, but I want to leave it out of this example to keep it more concise. But you're not really far. If you look at the slide, right at the bottom we have the function definition, what it looks like in Swift. And if you compare it to Objective-C, it is much more expressive. In Objective-C, we said we're going to take an object pointer to anything, we're going to turn it into JSON, and if it fails, we're going to crash. But here we take a JSON root object that expresses basically recursively all these different rules we had in the documentation. If you try this out, there's some more boilerplate code that goes into actually making this run. But if you try it out to see, if you try to construct another JSON object and pass it into this function, you'll get a compile error instead of a runtime error. I think it's incredibly useful and really a powerful example of modeling something much more expressive in the type system than was possible with Objective-C. So this wraps up the section on documentation and correctness. I think all of the examples have shown that we can catch a lot of errors at compile time instead of at runtime. And by having the type system express our constraints, we actually have an inherent documentation. I can use Xcode, I can command click on these types, and if I have some header docs on the types, then I'll have a really good understanding of what my JSON compatible values are without the have to find the documentation. If I'm dealing with a result type, I'll have a really good understanding that there can be two cases, and I don't have to go off and read the documentation on how to handle result and error in callback blocks. But now I want to talk about another way in which Swift and its type system has influenced how I write code today, and that is on a code design level. And in particular, I want to talk about how amazingly well I think protocols and generics in Swift go hand in hand. They're really cool tool. And what they allow us to do is they allow us to change how we share code between our types and our programs. I want to focus on one very specific example, and it has a very fancy term on the slide, and it's called subtype versus parametric polymorphism. I put up these fancy terms because I think it's useful if you want to do some research and learn more about them. But what I essentially mean is we're trying to replace subclassing, which is subtype polymorphism, with generics. Generics is parametric polymorphism. Why would we want to do that? In order to demonstrate that, I want to take an example that I've seen in a couple of apps, and I try to do the artificial example that resembles that. So the idea here is that we have some functionality that I kind of like to call vertical pillars. These are like the core things that your app can do. These might be downloading data, uploading data to a server, persisting data in the database. These are kind of fundamental infrastructure pieces of your app. And every app has some of these. In this example, I decided the downloader and a persistence layer would be what we use to walk through this. And the way you would implement this in Objective-C is typically we have some kind of base class. It would be a base downloader or a base data access object. And then you would have uppercase subclasses that kind of extend this behavior in some way. If you have a lot of different data types in your app and you want to download all of these, you want to store them in databases, then a lot of these types have a slightly different behavior, and you have to model that in some way. One of the classic ways was creating a subclass for all of these different types, and using subclassing as kind of an extension hook. So that the photo downloader can say, okay, I'm going to this specific URL, I'm calling this specific method to actually JSON encode or decode my data, and so on. So you would end up with what I call a type explosion. You have like these base types as vertical pillars, but then you have all these different subclasses for configuration. And you also end up in really weird places, like here in the bottom left you can see the snapshot downloader is actually subclassing the photo downloader. That's because that snapshot downloader is almost identical to the photo downloader. So instead of subclassing from the base class, we decided to use 2 levels of subclassing. And if you dealt with larger object-oriented code bases, you know that can cause a lot of different issues. Don't want to talk too much about subclassing because it's kind of a talk of its own, but there are definitely some problems here. And another one is redundant code, because you have a difficulty of kind of figuring out what code base is the base type and which code will actually have to have any subclasses in order to be able to configure it well enough. So I think it's worth we have a better way of dealing with this, and that is using parametric polymorphism through generics and protocols. So I took the same example and I replaced these base classes with generic types. And these generic types are now generic over protocols. So the downloader is generic over a downloadable type, and the data access object is generic over a persistible type. And these different conforming types that I showed earlier here, that need to configure that base behavior in some way, the post, the user, the photo, whatever data you're dealing with in your app, these can now use protocols to extend these types and to configure them in a certain way. So this is an alternative to subclassing, and I'm going to walk through a concrete example in the next couple of slides. So let's say we want to take this example and actually practically implement it. And for that example, I'd like to take a downloader that we want to build. So this should be a generic downloader that is able to download various different types. And we want to assume that we need different extension hooks, so we can define, for example, the source from which we want to download the data, how this data is maybe decoded from the network, and maybe also an extension hook that allows us to cache this data in some way. And for all these different extension hooks, for all the different ways in which you think you want to configure this generic type, you can define a protocol. And in this case, a protocol becomes something like a trait or a capability. That's trait is the name that I have in a lot of other languages. Because you're basically defining that my type can now participate in a certain action of my overall system. So you can define a downloadable protocol, and you can say that every type that is downloadable has to define the endpoint from which you're going to fetch the data. Then you can define a decodable protocol and say any type that is decodable has to provide an initializer in which it takes the data and it initializes itself, but it might also throw an error in case the data is inbound. Then you can define a cacheable type if you need something like this. That, for example, can say the type can define a caching duration, and if we have something stored on the client that is still within the valid time frame, then we won't even go to the network and try to fetch this data. So these are just a couple of examples of things you can choose how you want to parameterize this generic downloader type. So what would a downloader type itself look like? In the base example, it would look somewhat like this. It's a downloader class that is generic over type T, and that type T is downloadable. And this generic constraint at the top saying type T is downloadable gives us the ability to actually refer to the static type member that we earlier defined as part of this protocol. And that static type member is the endpoint URL. So you now would be able to, for example, define a very simple download function, and to keep this kind of easy, it is a synchronous download function that actually doesn't use asynchronous APIs. And this download function would take an identifier and return a piece of data that it downloaded from the network. This identifier in this example could be the ID of this object. So you might want to download photo number 15, then the identifier would be 15. And the downloader could now use this identifier together with the base URL that it gets from the type and combine it into a URL that it can use to request information from the network. So this is one example of how you can implement a generic type that uses information from one of the protocols that the conforming types provide. But we can also extend this. I talked about extension points, and I want to show you a couple of examples. So we said we have this cacheable protocol, and types might be cacheable. And if the type is cacheable, then we might want to have some different code inside of this generic type that actually performs some different effects. For example, it looks up if this data is stored in the cache. One mechanism to do that is using dynamic typecasting. And you can see that here in this line over here. What we're doing is we're checking if the type itself, the meta type, is a cacheable type. And that essentially checks if a type that is passed in here, if our T conforms to cacheable, and that indicates that it wants to be cached. And if that's the case, then we can access inside of this block here any properties that are defined as part of the cacheable protocol. So for example, we could look up how long does this type want to be cached, and then we could implement code based on that. So now we have this generic function, but it also has an extension for cacheable types where it performs some additional code. And this, you can see clearly how this is an alternative to actually having a cacheable downloader subclass. It's the same idea here. We're switching over the type and we're doing it inside the generic function instead of the subclass. And the third example shows how you can provide extensions where you want to actually provide a totally different API depending on the protocols which the type conforms to. So you could say if you have a type that is also decodable, then you could provide another function that says, instead of returning a piece of data, I actually use this data to initialize the type and create an instance of it. And that is possible because we define that any type that is decodable has to have an initializer that takes the data and returns an instance of itself. And then we're relying on this here in the last line. You can see we take this data from the generic download function, and in our extension we then use this initializer that is now available because our type is decodable and pass in the data and get back an instance. So that's another way how I can take a generic type and extend it based on conforming protocols. What would this look like from the type side, the place where we actually use these extensions? You would conform to these different protocols, and if you kind of write idiomatic Swift code, you would likely have one extension for each of these protocols to keep them somewhat separated in your code base. So the photo could say my endpoint URL is photos.example.com, my cache duration is 3,600 seconds, and here's my function that actually decodes me and takes the data and turns me into an instance of myself. I actually changed this last limit. The static function is now an initializer, but I actually missed to update the slide. But you get the idea. This is how the type would conform to the protocol. And what I really love about this is it is highly declarative. So instead of having a subclass where we have some code that is kind of hidden in the parent class, and we have to read all of the code to understand what's going on, we have a very clear extension that conforms to protocol that only has a few properties, and we very clearly define how these properties are set and how they influence the downloader type. And then we can put all of this together. We can create a downloader, and then we could just write some code like this that says I'm going to download a photo with an identifier Hawaii image number 2, and it would call this generic extension, and it would download the data, and then it would turn it into an instance of photo. So this slide is really just to show how these pieces fit together. So to summarize what I talked about in terms of code design, I think protocols and generics are really a great tool and a great alternative to subclassing. I hope that this example showed that it can provide a much cleaner extension mechanism. And really the two tools that I demonstrated are safe dynamic type checking, where you check if a type is cacheable and then perform some different code based on that. And the other one is constraint extensions that allows to actually provide an alternative API for types that conform to certain protocols. I'm getting close to end, but I want to get on to one more generic theme of all of this type business and static versus dynamic typing. And I also want to kind of address people that are maybe more comfortable in dynamically typed languages. I think one of the important things about type systems and when they become relevant is that their impact really grows with the size of the code base and the size of your developer team. If you have a very small project and you have all the constraints inside of your head, it's much easier to get started with a dynamic language and spin something up and get code that is working really quickly. When you work with types, you spend some type upfront defining types, defining generic arguments. You're trying to get the type system to understand the constraints of your software, it can be exhausting at times, but you kind of pay this infrastructure cost upfront, and later on you get a lot of benefits. By defining these types, if another developer comes into your code base, they will immediately see and understand how these types can be used and what your constraints are. One example is the result type. If you use that throughout your code base, then there will be a very clear pattern of what this result type means, and it's much more expressive in my opinion than the completion handler. And in another case, we have the downloader type that has these extensions in the form of protocols. I think it's much easier for someone to understand how they can create another type that is also downloadable, instead of understanding how they have to create another subclass and then copy code from other subclasses. But there is an upfront cost to it, and I think it's mostly worth it if you have a big code base. And in the proposal of this talk, I also mentioned that I'm going to talk about testing versus type systems, statically versus statically verified types, but I decided actually to cut this out because it's a topic of its own, but it bleeds a little bit into this whole idea of how types matter at scale. Anything you can verify in the type system is one test less that you have to write. So if you have, for example, an email type that I showed you earlier, you write one test that verifies that your email validation works correctly. You can use this email type throughout hundreds of different classes, and you never again have to write a test for it. And I think that becomes really valuable as your code base grows. That said, it's really hard to express things in the type system, much harder than it is to express ideas in tests. So you have to just consider how much of this upfront cost you want to pay, and that really depends on the size of your team and the size of the code base. So I talked about a lot of things. I'm going to summarize very briefly. I think the three key takeaways are that types are really great at documenting your system. They do that by being really expressive about the constraints, and I hope that the JSON example that I showed that kind of describes how JSON value can be encoded is one example. In that example, we had a type that defines exactly an array is encodable in JSON, a dictionary is encodable in JSON if these certain criteria are met. All of that was documented in the type system. We don't have to send off a developer to read documentation. And types-enabled correctness checks. I went through a couple of examples where we can eliminate a lot of runtime crashes by actually type checking stuff up front and getting the compiler to admit compiler errors instead. And I hopefully also showed how generics offer an alternative to subtyping. That is, in many cases, I believe, a better way of creating generic types that are extensible and can be used for multiple different types in your code base. I also talked about a lot of different concepts, and I put it up here in case you want to go back and learn more about them, because I really just touched on a very high level of use cases, but I didn't go into details. That's all I have for today. Thanks a lot for listening. I believe we have a few moments for questions. Is that true? Yeah. So in case anyone has questions, yes.
So, if I was understanding correctly, I believe that you used a protocol constraint and an extension for polymorphism, where you're replacing the implementation based on that constraint. Is that correct?
I used an extension to extend the API of the downloader.
So you replaced the download method?
No, so I'll repeat the question for the recording. The question was, I'm using an extension to replace a method. No, it's actually not possible in Swift, so you can't override a method in extension. But I'm actually overloading. I'm actually having a different type signature here on the function. So the core one returns a data, and this one returns a t. So the call side, depending on which return type you want, you will invoke one of these two functions.
Thanks.
Yep. Any other questions? Cool, I hope that's a good sign. Thanks a lot.